Good evening students, good evening. So welcome back, another class. What is the chapter name? Today's chapter name is Magnetism and Matter. We are starting a new chapter today, Magnetism and Matter. The attractive property and repulsive property of a magnet is concentrated at the ends. Students, we know that the attractive property and the repulsive property of a magnet is concentrated at the ends. These ends are called what? Poles. These ends are called what? Poles. A freely suspended magnet comes to rest. A freely suspended magnet comes to rest in what? North-south direction. We know that a freely suspended magnet comes to rest in what direction? North-south direction. Geography north-south direction. That is due to Earth magnetic field. All of you, good evening. Anaga, Shreya, Nandana, Vishnu Prasad, Aishwarya, Ismaya, Adira, Aliya, Anas, Anishri, Sweta. Good evening. The direction of magnetic lines of force is what? North to south outside the magnet and south to north inside the magnet. Suppose this is a bar magnet. The direction of magnetic lines of force is north to south outside the magnet and within the magnet south to north. So you should understand that magnetic lines of force can form closed loops because its direction is north to south outside the magnet, within the magnet south to north. A magnet can attract another magnet or magnetic substance, but a magnet can repel only what? Another magnet. See, what is the direction of magnetic lines of force? Its direction is north to south outside the magnet. Within the magnet is what? South to north. You can say that magnetic lines of force does not have source or sink. That means what? It doesn't start at any point, it doesn't end at any point. It doesn't start at any point, it doesn't end at any point. They are continuous closed loops. So its direction will be what? North to south outside the magnet and within the magnet south to north. So they are continuous closed loops. They doesn't start at any point, they doesn't end at any point. So that is the reason why we say that they doesn't have source or sink. A magnetic field lines can form closed loops. See, magnetic lines of force are forming closed loops. But what is the problem of electric lines of force? Its direction is what? Positive to negative. And it never goes to what? Negative to positive. So electric lines of force cannot form closed loops. But magnetic lines of force can form closed loops. Magnetic lines of force properties, they move away from north towards south outside the magnet. And within the magnet is south to north. The tangent to magnetic lines of force. Suppose this is a magnetic lines of force and this is north, this is south. Direction south to north inside the magnet, north to south outside the magnet. Suppose this is point A and if I draw a tangent here, this tangent will be the direction of magnetic field intensity at a point. The tangent to magnetic lines of force gives what? Direction of magnetic field intensity at a point. Two magnetic lines of force will never intersect with each other. Why? If they intersect, there will be two tangents at the point of intersection. Two magnetic lines of force never intersect. You know that the tangent to magnetic lines of force gives what? Direction of magnetic field intensity. If two magnetic lines of force intersect means what? If suppose they intersect at this point, one tangent will be, that is one direction of magnetic field intensity will be in this direction and another direction for magnetic field intensity will be in this direction, which is not possible. Why? Because a physical quantity cannot be at two different directions at the same point. So two magnetic lines of force will never intersect with each other. What is the problem? If they intersect, there will be two tangents at the point of intersection. Hence, there will be two directions for magnetic field intensity at the same point, which is not possible. So these are the properties of magnetic lines of force. See, properties of magnetic lines of force is very much similar to properties of electric lines of force. But the major difference is that magnetic lines of force can form closed loops, but electric lines of force cannot form closed loops. Magnetic lines of force doesn't have source or sink. That means they doesn't originate. That means they doesn't start at any point. They doesn't end at any point. They are continuous closed loops. But what is the difference in electric lines of force? Electric lines of force starts at positive charge, ends at negative charge, or its direction is positive to negative. Note ചെയ്യോ മക്കളെ? Please note down. Any doubts? എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടോ? ഇവിടെ തന്നെ വേറൊരു, you can say, add one more topic, one more point here. Suppose I got this material from earth. I have a suspicion, or I'm suspecting that I have a doubt that whether it is a magnet or not. Suppose I am bringing this black material to another magnet. Okay, if it is attracting, the black material is attracted to the magnet, then there are two possibilities. This black material can be either a magnet or magnetic substance like iron. And suppose this black material, when I bring that black material close to another magnet, if this black material experience repulsion, if this black material is experiencing repulsion, then we can be 100% sure that it is a magnet. So you can say that repulsion is the sure test of magnetism. Repulsion is the sure test of magnetism. Repulsion is the sure test of magnetism. That is our next point. Repulsion is the sure test of magnetism. What is the use of these chapters? Anas, we are able to identify magnetic phenomena. We are coming to know that Earth behaves like a magnet. Okay, so we are understanding the magnetic properties. In the fourth chapter, we came to know that whenever there is a current flow, there will be magnetic field. In this chapter, we are analyzing magnetic field. What are its properties? What is its strength? And what are the different types of magnetic material that we will be understanding in this chapter. Okay, note it down. ആ സ്ക്രീൻ നോട്ട് ചെയ്യുക കേട്ടോ. വളരെ ഇമ്പോർട്ടൻ്റ് ആയിട്ടുള്ള, വളരെ ബേസിക് ആയിട്ടുള്ള കാര്യങ്ങൾ അതിൽ കൊടുത്തിട്ടുള്ളൂ. This screen is all about magnetic properties, differences between electric lines of force and magnetic lines of force. Any doubts? Anybody, any doubts? Yeah, please note it down. Hello? All of you, please note down. Electric lines of force cannot form closed loops. Magnetic lines of force can form closed loops. How Earth behaves like a magnet. See, Shreya, there was a topic called Earth magnetism and matter. Earth magnetism. That topic, that section got deleted from the NCERT textbook. So there is a topic called dynamo effect. Everything got deleted. It's not there for entrance also. So I'm not explaining that because it got deleted. Before Corona, that topic was there. Figure വരയ്ക്കണം. Yes, yes. You have to draw the figure. The attractive property and repulsive property of a magnet is concentrated at ends called poles. Done? All of you done? Done, right? Next, I am doing a comparative study between electric field and magnetic field. See, remember, electric dipole. See, I am comparing first chapter with the fifth chapter. Electric dipole. What is electric dipole? Equal and opposite charge separated by a distance 2a. Okay. What is magnetic dipole? Equal and opposite poles. Equal and opposite poles separated by a distance. In magnet case, we call distance as 2L. So what is the here? Strength of a pole is called pole strength. What is the equation for pole strength? P is equal to Q into 2L. P equal to Q into strength of a pole is called pole strength, denoted by P. Unit of pole strength is ampere meter. Unit of pole strength is ampere meter. Similarly, in electric dipole case, equal and opposite magnetic poles separated by small distance constitutes magnetic dipole. Magnetic moment M is equal to pole strength P into 2L. Remember, in electric case, strength of electric dipole is electric dipole moment denoted by letter P. P is equal to, what is the formula? Q into 2A. So what will be the unit of P? Unit of electric dipole moment. Charge unit coulomb. Distance unit is what? Meter. Coulomb meter. See, in the first chapter, P is electric dipole moment. In this chapter, that is 5th chapter, what is P? Pole strength. What is its unit? Ampere meter. In first chapter, P is dipole moment. In 5th chapter, M is what? Magnetic dipole moment. How magnetic dipole moment is calculated? Pole strength. See, if north pole is having pole strength P, then magnetic moment will be what? Pole strength into distance between the poles. So what will be the unit? Pole strength ampere meter into distance between the poles meter. So ampere meter square is the unit of magnetic moment. Any doubts? Now, direction of electric dipole moment is towards positive charge. So minus Q charge plus Q charge, direction of electric dipole moment is what? Towards positive charge. That is the direction of electric dipole moment. Then direction of magnetic moment is see, north south. Direction of magnetic moment is what? Towards south. Direction of magnetic moment is what? Moment is towards south pole. Towards south pole. Any doubts? Sir, unit പറയുമ്പോൾ അതിന്റെ dimension കൂടി പറയാമോ? Yeah, okay. ഇനി തൊട്ട് ശ്രദ്ധിക്കാം. So towards south pole. Actually, why I am not telling is it's a regular +2 class. In +2 regular class, dimensional formula is not required. It is required for entrance only. Okay, no problem. So, magnetic moment is what? Direction of magnetic moment is what? Towards south pole. Direction of electric dipole moment is what? Towards positive charge. Now, suppose this is dipole minus Q charge plus Q charge, the separated distance by 2A, and from the mid of the dipole, if you consider a point, this is what? Axial point. And this will be what? Equatorial point. That you might, we already know that. We have proved that electric field incident axial point in the equatorial point. And similar to magnet, in the magnet case also, suppose this is north, this is south, this is pole strength P, separated away distance of what? 2L. So this much distance is what? R. So here we will get what? B axial along the axial point. And here we will get what? B equatorial. So I am understanding from these figures, I am understanding that in electric case also magnetic case, both are same. E axial, B axial are same. Electric field incident axial, electric field incident equatorial. Concept is same. I am not saying the equation is same. Concept is same. So, okay. What is the equation for electric field incident axial point of a dipole? 1/4 pi epsilon naught. What is equation? 2PR divided by R square minus A square the whole square. See, we have already derived this equation in the first chapter. I am just repeating this topic in order to make sure that you remember the first chapter topic, and I am establishing a connection between first chapter and the 5th chapter. So what will be B axial? So mu 0/4 pi. There it was electric dipole moment P, here magnetic moment M. So 2mr by r square minus L square the whole square. I hope you got the connection. Here derivation is deleted, only final answer is required. I hope you got the connection. Now E axial special case is what? 1 by 4 pi epsilon naught 2p by r cube. B axial special case is what? 1 by 4 pi epsilon naught 2m by r cube. Here r much greater than A. Here r much greater than L. Any doubts? Any doubt? Any doubts? We have done this, no? So we are understanding that electric field, magnetic field equations are almost same. Only difference is that in electrostatics chapter we have electric dipole moment P, but in magnetism and matter we have magnetic moment M. In electric case, the distance is in order to represent the distance between the dipole, we use the variable 2a, and here we use the variable 2l. So it is very much similar. So I am just comparing these two chapters so that you can learn both the chapters at the same time. Any doubt? Any doubt? മക്കളെ ഡൗട്ട് ഉണ്ടോ? റെസ്പോണ്ട് ചെയ്യൂ. മക്കളെ ഡൗട്ട് ഉണ്ടോ? നോ സാർ ക്ലിയർ. നോ സാർ ക്ലിയർ. നോട്ട് ചെയ്യട്ടോ. ശ്വേത, അനസ്, കപില, ക്ലിയർ റൈറ്റ്? Anas, I hope you don't have any doubt. Noted? B axial mu by 4 pi. Ayo, sorry. See, I made a blunder here. So thank you for pointing out. I think all of you know that it is mu 0 by 4 pi. Thank you. Thank you. Mu 0 by 4 pi it is. Any doubts? Yeah. Sorry. Corrected that. I have corrected. Thank you, Shifana and Sharanya. Please, all of you, please correct that. Done. Please finish fast. Please understand also because we are continuing. Yeah, done. Yes, sir. Done. Okay, let's continue. Now, in electric case, E axial is equal to 2 times E equatorial. In similar way, B axial is equal to what? 2 times B equatorial. In electric case, the work done in rotating an electric dipole from its position of stable equilibrium the work done rotating an electric dipole in a uniform electric field. The work done in rotating an electric dipole in a uniform electric field is work done is equal to, equation is PE into cos theta 1 minus cos theta 2. What is the equation for work done? Work done in rotating an electric dipole in a uniform electric field from its initial angle theta 1 to final angle theta 2 is Now, that is what? P into cos theta 1 minus cos theta 2 that we have done in the first chapter. So, same thing comes in fifth chapter also. The work done in rotating what? A magnetic dipole in a uniform magnetic field from initial angle theta 1 to final angle theta 2. Final angle theta 2 will be, what is equation? Work done is equal to MB into cos theta 1 minus cos theta 2. What is B? Magnetic field. What is E? Electric field. What is P? Electric dipole moment. What is M? Magnetic moment. Next, the torque experienced by, see, again derivation is not required, only final answer is required. The torque experienced by an electric dipole an electric dipole in a uniform electric field is torque tau vector is equal to P vector cross E vector. Torque tau vector equal to P vector cross E vector. The torque experienced by that is torque equal to what? PE sin theta, because we know that A vector cross B vector is AB sin theta. So P vector cross E vector PE sin theta. The torque experienced by a magnetic dipole placed in a uniform magnetic field is what? Uniform magnetic field is torque tau vector is equal to M vector cross B vector. Torque equal to what? MB sin theta, where M is what? Magnetic moment. So we have compared both electric and magnetic case. Any doubts? Any doubt here? Any doubt? Now always remember, this torque is stored as what? Potential energy. So potential energy U is equal to what is the equation? Potential energy U is equal to what? In electric case it is P sin theta. In magnetic case potential energy U is equal to what? MB sin theta. This torque, not this torque, what I have written, not this torque, actually it is a work done. Sorry. Not torque is stored as, it should be work done is stored as potential energy. So there is a mistake from my side. Not work done stored as potential energy. So potential energy is equal to U equal to PE into cos theta 1 minus cos theta 2. And here it becomes what? Work done. Again here also work done is stored as potential energy. Potential energy U is equal to MB into cos theta 1 minus cos theta 2. Any doubt? Any doubt here? Work done is stored as potential energy. I substituted it for torque, which was wrong. Work done is stored as potential energy. I hope it is clear. Please note it down. Noted, done. Noted, right? All of you done? Yeah. So next is continuing. So potential energy is equal to minus P cos theta in the electric case. See, work done is equal to what is the equation? PE into cos theta 1 minus cos theta 2. This work done is stored as potential energy. So potential energy is equal to P into cos theta 1 minus cos theta 2. Now, if dipole is at an angle theta, suppose simply one angle is given, angle theta with the electric field. In that case, the potential energy, work done, potential energy will be what? Minus P cos theta. If magnetic dipole, first one was electric dipole, magnetic dipole is at an angle theta with the magnetic field, then potential energy will be what? Minus mb cos theta. Potential energy will be what? Minus mb cos theta. In the magnetic case, this is the electric case. This is the electric case. And this is the magnetic case. Potential energy equal to what? Minus mb cos theta. Now, if dipole, I am simply writing dipole, it can be electric or magnetic. If dipole is in the direction of electric field or magnetic field. If electric dipole is in the direction of electric field or magnetic dipole is in the direction of magnetic field, then theta will be what? 0. This is called stable equilibrium. Stable equilibrium. What is the specialty here? Potential energy will be minimum. Potential energy will be minimum. So U equal to what? Minus mb into cos 0. Cos 0 is equal to what? 1. So U equal to what? Minus mb. In the magnetic case, in the electric case, what will be? U equal to what? Minus PE in the electric case and in minus mb in the case of magnetic case. If theta is equal to, this position is theta 0 means what? Parallel. Theta 0 means what? Dipole is parallel to the electric field. If dipole is anti-parallel to electric field or magnetic field, theta will be what? 180 degree. That is what is anti-parallel. So potential energy is equal to what? Minus mb into cos 180. Cos 180 is equal to what? Minus 1. So potential energy is equal to what? Minus mb into minus 1. So u equal to what? Plus mb in the magnetic case, and u equal to what? Plus pe in the electric case. I hope it is clear. This is the when the dipole is anti-parallel to electric field or theta equal to 180. This is called, the situation is called what? Unstable equilibrium. This situation is called what? Unstable equilibrium. And what is the specialty here? Potential energy will be maximum. Maximum potential energy in the unstable equilibrium and minimum potential energy will be in the stable equilibrium. Any doubts here? See, we are just comparing the first chapter and fifth chapter and writing the equation. Equations are almost, means everything, every equations are same. Only difference is what? In the first chapter we have what? Electric dipole moment is P, and the fifth chapter we have what? Magnetic moment is M. Any doubt? Any doubts? All of you done? Noted? All of you noted? Yeah, continuing. കഴിഞ്ഞില്ലേ? Clear അല്ലേ? അല്ലേ? നോട്ടഡ് അല്ലേ? ശരി. അടുത്തത് പ്രോബ്ലം ചെയ്യാം. വാട്ട് ഈസ് ദ വർക്ക് ഡൺ in rotating an electric dipole from its position of stable equilibrium to unstable equilibrium in an external uniform electric field. Uniform electric field. See, what is the work done they are asking? What is the equation for work done? PE into cos theta 1 minus cos theta 2. So, here initially theta 1 equal to 0 degree, cos 0 is equal to 1. Finally, final position, theta 2 is equal to what? Stable to unstable. Unstable means what? Anti-parallel. So, theta 2 is equal to 180 degree, cos 180 is what? Minus 1. So, work done is equal to PE into cos 0 minus cos 180. That is PE into 1 minus minus 1. So, PE into 2. So, what is the answer? Work done is equal to what? 2 PE. Now, suppose they are asking for potential energy. What will be the potential energy? That is also 2 PE because work done is stored as what? Potential energy. Positive and the are unstable. See, initially stable. Stable means what? Dipole in the direction of electric field. So, theta 1 0. Finally, unstable. Unstable means what? Anti-parallel. Anti-parallel means what? Theta has to be 180 degree. Why? I will show that. Suppose this is electric field and this is the dipole. Suppose this is plus Q and this is minus Q. What is the direction of dipole moment? It is towards the positive charge. So, when you examine this, you can understand that electric field and dipole are in the opposite direction. So, theta is equal to 180, which is the unstable equilibrium, and cos 180 is equal to in the minus 1. Any doubt? Sharanya, അത് മനസ്സിലായോ? മനസ്സിലായില്ല? ഇലക്ട്രിക് ഫീൽഡ് അങ്ങോട്ടും ഡൈപോൾ മൊമെന്റ് ഓപ്പോസിറ്റ് ഡയറക്ഷനിലും. അപ്പൊ തീറ്റ എത്രയാ? 180, കോസ് 180 എത്രയാ? മൈനസ് 1. ഓക്കെ, നൗ വാട്ട് ഈസ് ദ വർക്ക് ഡൺ in rotating a magnetic dipole from its position of stable equilibrium to unstable equilibrium in an external uniform magnetic field. Okay, first you note down this problem, then note down complete this problem. I am not writing the answer here. You have to write your answer yourself. Please do it yourself. 2 MB, yes. All of you got the right answer, 2 MB. Work done is equal to what will be the answer? Work done is equal to MB into cos theta 1 minus cos theta 2. Now M is magnetic moment. MB initially is what? Stable. So theta 0 cos 0 minus finally is what? Unstable cos 180. So work done is equal to what? MB into cos 0 1 minus cos 180 minus 1. So work done equal to MB into 2. So work done is equal to what? 2 MB. What is work done? 2 MB. Any doubts? Doubt unda? Note ചെയ്താ? I hope there is no doubt. Now, when current passes through a solenoid, we know that it behaves like a bar magnet. Behaves like a bar magnet, that we know. When current passes through solenoid, it behaves like a bar magnet. So there will be, if it is a bar magnet, then there will be what? Magnetic moment. There will be magnetic moment. That equation for magnetic moment M is equal to IA, I into A. Magnetic moment M equal to what? I into A. Magnetic moment M equal to what? I into A. Please remember, equation for magnetic moment when current passes through a loop. What is the formula for magnetic moment? IA. Why there is magnetic moment? Because when current passes through a loop, what happens? It behaves like a bar magnet. If it is a bar magnet, then it should have what? Associated magnetic moment. And what will be the formula? Unit will be same, because current is what? Ampere. And A is what? Area. So again the same unit only, ampere meter square. See, there is one more unit for magnetic moment, that is Joule per Tesla. Moment. There is another unit called Joule per Tesla. In some problems, you can see magnetic moment represented as Joule per Tesla. So please remember, there is another unit, Joule per Tesla. Okay, magnetic moment Joule per Tesla. Any doubts? Now, if there are n turns, then magnetic moment M is equal to NIA, number of turns into current into area. Number of turns into current into area. Now, Gauss's law in electrostatics. I am just repeating that. Gauss's law in electrostatics. The total electric flux through any closed surface enclosing a charge is equal to 1 by epsilon 0 times the total charge enclosed. We know that formula. We know that phi is equal to phi suffix e is equal to integral over s e vector dot ds vector is equal to 1 by epsilon 0 times q. I think explanation is not required. What is phi suffix C? Electric flux, which is number of lines of force passing normally through an area. Electric flux unit is what? 1 unit Newton meter square per coulomb. Another unit is what? Volt meter. These are the two units for electric flux. This is Gauss's law in electrostatics. Now my question is that if a closed surface contains an electric dipole, what will be the total electric flux through it? Phi suffix C is equal to integral over S E vector dot ds vector is equal to 1 by epsilon 0 times total charge. But remember, total charge of a dipole is what? 0. So, total electric flux will be what? 0. Navaneet, A endinde area ആണ് ആ ക്ലോസ്ഡ് നമ്മൾ കൺസിഡർ എ എന്ന് പറഞ്ഞാൽ എന്താ ആ സർക്കുലർ ഇവിടെ കറന്റ് ക്യാരിങ് ലൂപ്പ് ഇല്ലേ ആ കറന്റ് ക്യാരിങ് ലൂപ്പിന്റെ ഏരിയ ആണ് എ ഓക്കെ ആ കൺസിഡർ ചെയ്യുന്ന ലൂപ്പിന്റെ ഏരിയ ആണ് എ അപ്പോൾ ഒരു ക്ലോസ് സർഫസിലുള്ള ഇലക്ട്രിക് ഡൈപോൾ ആണെങ്കിൽ ടോട്ടൽ ഇലക്ട്രിക് ഫ്ലക്സ് എത്ര ആയിരിക്കും 0 ആയിരിക്കും കാരണം വാട്ട് ഈസ് ദ റീസൺ ബിഹൈൻഡ് ദാറ്റ് ഇഫ് 5 coulomb positive charge is there 5 coulomb negative charge will be there so total electric flux will be 0 similar to that Gauss's law in magnetism what is Gauss's law in magnetism the total magnetic flux through a closed surface containing a bar magnet is 0. Why we are saying that? See, suppose a closed surface contains a bar magnet. So, if there is north pole equal and opposite south pole is there. So, total magnetic flux is equal to what? Integral over S B vector dot ds vector is equal to what? 0. Why is equal to 0? Because north pole strength will be cancelled by whom? South pole strength. So, total magnetic flux will be what? 0. Similar to what? Total electric flux through a closed surface which contains a dipole. Electric dipole. Any doubt? Gauss's law in magnetism very important. Gauss's law in electrostatics is also very important. Any doubts? കുട്ടികളെ നിങ്ങൾ റെസ്പോണ്ട് ചെയ്യണം ഇമ്പോർട്ടൻ്റ് ആണ് മനസ്സിലായില്ലെങ്കിൽ ഞാൻ ആദ്യം എടുക്കും വളരെ ഇമ്പോർട്ടൻ്റ് ആണ് പ്ലീസ് റെസ്പോണ്ട് ഇഫ് യു ആർ നോട്ട് ഏബിൾ ടു അണ്ടർസ്റ്റാൻഡ് ഐ വിൽ റിപ്പീറ്റ് ബിക്കോസ് ടോപ്പിക് ഈസ് വെരി ഇമ്പോർട്ടൻറ്റ് Please, students, respond. All of you understood Gauss's law in electrostatics and Gauss's law in magnetism. It's important, very important. Clear and noted. Anas, Gauss's law once more. Gauss's law in electrostatics or magnetostatics? Anas. Sir, bar magnet dipole is similar. So, in application of Gauss's law, we consider closed cylinder, sir. There is some electric flux. How come here it is 0? Sweda, in the application of Gauss's law, we considered closed cylinder, but inside the closed cylinder, it was not electric dipole. It was a single positive charge or a long straight current charged wire having linear charge density. In that case, there was only positive charge, no negative charge. If there is positive and negative, then the total will be 0. I hope it is clear, Sweda. Please respond. Yeah, now Anas want me to repeat that Gauss's law in magnetism. See, Anas, suppose it's a closed surface and I have a bar magnet within this closed surface. What will be the total magnetic flux? Find out magnetic flux through small area ds. Then what? Integrate. That is the way to find out total magnetic flux. So it becomes what? Integral over S B vector dot ds vector. Now the problem is that, not problem, the situation is that if there is north pole is having a particular pole strength, south pole is having what? Equal and opposite pole strength. So they will cancel with each other and your answer will be what? 0. Which means what? The magnetic monopoles do not exist. Magnetic monopoles do not exist. You can't simply take a single pole. Magnetic monopoles do not exist. If magnetic monopoles, mono means what? Single pole, then right hand side RHS will not be 0. RHS is 0 means what? If there is a north pole, there will be obviously there will be a south pole. Then only you will be getting a total magnetic flux 0. So, Anas, if you have a bar magnet, you are putting that bar magnet into mixie and the mixie is cutting the bar magnet into maybe 1000 parts. Then each part is having north pole and south pole. You cannot get a single monopole. Ottapole, mono means single. You won't get a single pole. So, the simplest element of magnetism is simplest element of magnetism is dipole. You cannot divide a dipole further. You cannot divide a dipole and make two monopoles. That is not possible. That is what is telling you by Gauss's law in magnetism. Please note it down. I hope it is clear. Done? Okay, noted. So Gauss's law in magnetism is also done. Then what else? Let's do some problems. Okay. A magnetic dipole of length 10 centimeter has pole strength of 20 ampere meter, has pole strength of 20 ampere meter. Find the magnetic moment of the dipole. Find the magnetic moment of the dipole. Magnetic moment of the dipole. Magnetic dipole of length 10 centimeter. So dipole length, always remember, dipole length we represent it as 2L. So given 2L is equal to what? 10 centimeter, which is equal to 0.1 meter. Pole strength is what? P, that is equal to what? 20 ampere meter. Find the magnetic moment M equal to question mark. It's very easy. M equal to, we know that M equal to P into 2L. What is P? 20. 2L is what? 0.1. 20 into 0.1 is what? 0.2 ampere meter square. Twenty into 0.1 is 2. Sorry. 2 ampere meter square. 2 ampere meter square. Any doubt? Any doubt? Doubt now? Clear? Next problem. A bar magnet of magnetic moment a bar magnet of magnetic moment 5 ampere meter square has poles 20 centimeter apart. 20 centimeter apart. Calculate pole strength. We have to calculate pole strength. Question mark. Pole, sir, how magnets exert force without any contact? See, first of all, I don't know who is entering the class in Cosmos ID. It is not necessary that in the definition of force is an agency which changes or tends to change state of rest or state of uniform motion or direction. Even if it is direction is changing, we call it as force. So it is not necessary that there should be a physical contact to happen for the definition of force. So magnetic force, repulsion time, even though there is no physical contact, we still call it as a force because it is not necessary that there should be physical contact. Cosmos. Svera got, what about others? Magnetic moment. So M is equal to what? 5 ampere meter square. 2L is equal to what? 20 centimeter, that is 0.2 meter. So M equal to P into 2L. So P is equal to M by 2L. M is what? 5 divided by 2L is 20, that is 0.2. That is 50 by 2, that is equal to 25. Since it is pole strength, unit is ampere meter. Got it? All of you got it? Done? I hope it is done. So next topic. What is the magnitude of the equatorial and the axial magnetic fields due to a bar magnet of length 5 centimeter at a distance of 50 centimeter from the midpoint. 50 centimeter from the midpoint. The magnetic moment of the bar magnet is 0.4 ampere meter square. Now let's see magnitude of the equator and the axial magnetic field due to a bar magnet length. So bar magnet length is what? 2L. This is north pole, this is south pole. That 2L is given as what? 5 centimeter. So that is equal to 0.05 meter. That is the distance between the poles at a distance 50 centimeter from the midpoint. So from the midpoint distance is what? 50 centimeter. In our formula it was R. The distance from the midpoint was R. R equal to 50 centimeter, which is what? 0.5 meter. So from this data I am understanding that R much greater than L. So in order to find the magnetic field at axial point, I should be using the formula mu0 by 4 pi 2m by r cube. Special case of formula, since r much greater than L, and it is also given that magnetic moment is 0.4 ampere meter square. So mu0 is 4 pi into 10 raised to minus 7 divided by 4 pi into 2 into 0.4 divided by r is what? What is the distance? It is 50 centimeter, that is 0.5 cube. 0.5 cube. If you solve that, you will get the answer 3.2 into 10 raised to minus 7 Tesla. Since we are finding out magnetic field, your answer should be 3.2 into 10 raised to minus 7 Tesla. That was about axial point. Now let's see equatorial point. B equatorial is equal to mu 0 by 4 pi m divided by a square plus r square whole raised to 3 by 2. What is mu 0? 4 pi into 10 raised to minus 7 divided by 4 pi into 0.4. Oh, not a square, not a square. A square in the first chapter case, it should be L square. No, even not, that is not the case. Sorry. It is special case, right? Because R is much greater than. So mu 0 by 4 pi m by r cube is enough since R greater than L. So mu 0 4 pi into 10 raised to minus 7 divided by 4 pi m is 0.4 divided by r cube is, right? R cube is what? 0.5 the whole cube. So if you solve that, you will get 6.4 into. No, there is a mistake from my side. See, there is a mistake from my side. When I copied the answer, equatorial answer is 3.2. Equatorial answer is 3.2 into 10 raised to minus 7 Tesla. Axial answer is 2 times of that. So 6.2 into 10 raised to minus 7 Tesla. 0.05 0.5 comparable അല്ലേന്നാ. അതെങ്ങനെയാണ് കമ്പയർ ആവണേ? 0.5 by 10 അല്ലേ? 0.05 or you should say 0.05 10 times അല്ലേ 0.5. അതെങ്ങനെ കമ്പയറബിൾ ആവണേ? അത് കമ്പയറബിൾ ആവില്ലല്ലോ നവനീത്. Doubt undo? Any doubts? Anas, Sweda, any doubts? Saranya, Agash, Alanchand, Navaneet. Doubt undo? Noted? Is it noted? Okay, there is no doubt. Do you guys finish that? Yeah. So let's do the next problem. More tough one. A bar magnet of length 10 centimeter, has a pole strength of 10 ampere meter. Calculate magnetic field at a distance of 0.2 from its center. First axial, second equatorial. Okay, let's see. So this is the bar magnet, north, south, distance is what? 12. 12 equal to what? 10 centimeter, that is equal to 0.1 meter. Pole strength is what? What is the pole strength? 10 ampere meter. Okay. Calculate magnetic field at a distance. Distance means what? R equal to what? 0.2. Distance of 0.2, is it meter or 0.2 meter? 0.2 meter. നാളെ നോർമലായിട്ട് വർക്കിംഗ് ഉണ്ട് കേട്ടോ, മീൻസ് നോർമൽ ക്ലാസ് ഉണ്ടാവും കേട്ടോ, റെഗുലർ ക്ലാസ് നാളെ രാത്രി 7 മണിക്ക് എൻ്റെ ഫിസിക്സ് ക്ലാസ് ഉണ്ടാവും കേട്ടോ. മൊഹറായിട്ട് വ്യത്യാസമൊന്നുമില്ല, എൻ്റെ ക്ലാസ് ഉണ്ടാവും. അപ്പോൾ ആർ ഈസ് വാട്ട്? ഡിസ്റ്റൻസ് ആർ ഈക്വൽ ടു 0.2 മീറ്റർ ആണ്. ദിസ് ഈസ് മീറ്റർ. And we have to find out that axial point. So B axial is equal to, now what is the L value here? L value is 0.1, R value is 0.2. So it's almost same only. So we should go for the traditional formula, that is mu 0 by 4 pi 2n R divided by R square minus L square the whole square. So 4 pi into 10 raised to minus 7 divided by 4 pi into 2 into, what is the magnetic moment? 10 into, magnetic moment M equal to what? P into 2L. So 10 into 0.1 into distance R is what? 0.2 divided by 0.2 the square minus L is what? L is 2L is 0.1. So L is what? 0.1 by 2. So 0.05 the square, the whole square. 0.05 square, the whole square. So if you solve that, I am directly writing the answer 2.84 into 10 raised to minus 5 Tesla. I hope there is no doubt. Now B equatorial will be what? Mu 0 by 4 pi. What is the formula? Mu 0 by 4 pi M divided by R square plus L square whole raised to 3 by 2. So 4 pi into 10 raised to minus 7 divided by 4 pi. Instead of M, I should write what? M equal to P into 2L. So P is 10 into 2L is what? 0.1 divided by R is what? 0.2 square plus L is what? 0.05 the square whole raised to 3 by 2. If you substitute, you will get the answer. I am directly writing the answer 1.14 into 10 raised to minus 5 Tesla. I hope it is clear. Any doubts? Any doubts? Here we are using the traditional formula, the standard formula, because R is almost similar to what? L. Any doubts? Please note down. So I will see you tomorrow. Thank you. ആ മറ്റേ ബുക്ക് അവിടെയൊന്നും ഇല്ല.